Hi everyone, welcome to my channel. This is Leo and let's do some more Leetcode problems today. Today's problem is called linked list in binary tree. We were given a binary tree root and a linked list with head as the first node. Return true if all the elements in the linked list starting from the head correspond to some downward path connected in a binary tree, otherwise return false. So in this context, downward path means a path that starts at some node and goes downwards. So this is pretty easy to understand. Let's see it in an example here. We have a binary tree rooted at 1, and we have a linked list starting from 4 and goes to 8. So the problem is, can we find a downward path that contains all the nodes in the linked list? Okay, so how can we find this problem? So first we have to make sure, since we're going for a downward path, we can use DFS traversal. Okay, so basically DFS goes from the root and goes down all the way to the root to the leaf node, and then goes back and traverses to the other side until it hits another leaf. It traverses back and then hit another leaf, back, another leaf, and then goes back to the root. Okay, so that's how DFS works. And since we're looking for a downward path, we have to use the DFS. Okay, and next is to find the head node in the binary tree. Okay, so we can check if this is the head of the binary of the linked list. Okay, if it's not, we can go left or right to find the head. Okay, once we find the head, we can run another function to check whether the full linked list exists here. Okay, so we need another function. So once the head is confirmed, run the check function to find the full path. Okay, so in this case, let's walk it through here. So is it 4 the head? No, so we can go left or right. Okay, we can go left first. Is it the 4? Yes, good. Now we don't explore any further. We can run another function here. So we can check if it contains the full path of the linked list. Okay, so let's see, we have a 4 here. Okay, then we move ahead to the linked list, so we go to 2 and we explore, is there a 2 in the subtrees? Yes, it is. Okay, so we can come here. Next, we're going to find 8. Is there a subtree that contains the node 8? No. So this path doesn't work. Okay, so here at 4 we return false. Okay, and then after that we go on to explore the head of the linked list. Okay, so we go down. Is it 4? No. Is this 4? No. So this full path is explored and will return false in the left subtree. Okay, so we go right. Same here. Is it the head? Yes. So we call another function to check the full path. So we move ahead in the linked list. We go to 2. And is there any left subtree or right subtree that contains the node 2? Yes. So we move ahead and we look for 8. Is there an 8 in left or right subtree? Yes. So we move here. Now we're at the end. Okay, so is it the full path? Yes, so we return true here. Okay, so yeah, that's how we find it, and I think this is pretty much the same, so we can now code it out, right? So first we will use a DFS function. So basically how we write it is we have a base case. Okay, so for this function, if we don't have a root, that means if we don't even have a binary tree, we will certainly return false. Okay, and if head equals to null, we'll return true because it will exist everywhere. And then we can run the check to see if it is the path head. Okay, check head. So head root. Okay, and next check head. So I will copy it from here. Okay, good. So if root equals to null, we will not have a binary tree, so we'll return false. Okay, and if head is the if current node is the head, we'll run a DFS check. Okay, so we will path check. Let's call it path check, and root with the current head. Okay, so if this is the truth, we return true. Okay, otherwise, if current node is not the head, explore subtrees. Okay, so we will return check head root on left, or check head, sorry about the typo here, check head root on right. Okay, so if any of the subtrees has the head, we can run the path check there. Okay, so next we can run the path check. I think it's still the same signature. So here some things becomes a little bit tricky. So if we have head equals to null, we can return true. Why is that? Since we're at here, and we can go next, but next we have the node in the binary tree, but we don't have a head because head will be pointing to null here. Okay, so if it points to null, that means we have explored the full path, so it must exist here, so we can return true. All right, and there's another scenario where the root equals to null. So for example, if we have a path like 4, 2, 8, 3, 5 for the linked list. Okay, so now here we check 4, 2, 8, 3. Okay, everything good. Next, head will be pointing to 5, but do we have any subtrees left? No, we don't have anything left. That means we cannot contain the full path here. So in this case, we'll return false. Okay, and there's another option here. So another point to check. If the root node is not the head, the value that head pointing to. So that means if root.value doesn't equal to head.value, of course we'll not go through this path. Okay, return false. Okay, otherwise we can go left or right to check if it matches the next node in the linked list. Okay, so path check, head on next, root on left, or path check, head on next, root on right. Okay, so for DFS traversal, it's pretty simple. You just have to think about what you're going to do in our current layer and what to do in the next layer. Then what we want from the next layer, like what information do we need from the next layer, and define a base case, which is the termination condition. Okay, let's run it. Hopefully it works. Okay, yeah, I think it worked. So let's analyze the complexity here. For time complexity, in the worst case, we're traversing through all the nodes, so it should be n. And if we have multiple nodes that suits to the head, we will run the check full path algorithm for all the nodes here. Okay, so in the worst case, it could take up to n by m time to do this. So where n is the number of nodes in the binary tree and m is the length of the linked list. Okay, so we have to explore each node, and for each node we have to run the path check. Okay, so that's the worst case. For space, I think since we're using DFS, we're only having the call stack. Okay, so in the worst case, it would be O of n for the binary tree, the call stack, and we will have the check full path function, which takes up to O of m space. Okay, so in the worst case, it will be n plus m for these two functions. Okay, yeah, let's submit it to see if it works. Okay, perfect. Thank you so much for watching. I hope this video is helpful to you. And if you like the video, please like and subscribe to my channel. I'll see you in our next video.